So the next topic we're going to cover is looking at a bunch of example applications that demonstrate some of the interesting properties of fork join pools. And unlike the earlier examples we've looked at that tended to focus on some variant of search stream gang that used streams or parallel streams or whatever, this example is going to look at something different. And the reason we're going to look at something different is we want to tease out other aspects of fork join pool that might not manifest themselves by just doing yet another variant of the search stream gang program. So what we're going to do here is we're going to have a little example application, which you can download in the EX22 folder in my GitHub repository, that will implement operations on big fractions using a bunch of different fork join pool programming models. And a big fraction is just an arbitrary precision fraction class. Okay, so what we're going to do is we're going to run this program here. And the program is going to demonstrate a whole bunch of different things. It's going to show you the performance of the different approaches applying the fork join pool in different ways. And I'll go through all the different approaches here in a minute. And what it does is it runs a bunch of different approaches, and then it goes ahead and it prints out the results in terms of how long things took to run, how long it took to do the processing. And you can see that there are differences in the performance. And the other thing that it prints out are some statistics that help explain why the different approaches perform in different ways. In particular, it gives you the steal count for each of these things. That's how threads are stealing stuff from other threads. So we'll talk about that. And what you'll see is that the different approaches will look at some approaches incur more stealing, some copy more data, some make more method calls, and there's all kinds of different pros and cons of this. I should probably, when I revise this slide, I'll probably blow this up so it's a little bit easier to read. It's kind of hard to see that from where you're sitting, I'm sure. I can hardly see it looking in the back. We use a couple of functional programming features and Java streams, sequential streams, just to simplify the driver code. But as we'll see, for better or worse, the use of the fork join framework is typically a bit more object-oriented than we might want because of the fact that Java 8 introduced the functional features, but fork join pool came out in Java 7. So it didn't have the benefit of using those features, unfortunately. OK, here's the main program. This is kind of the driver. This is the one that will reduce and multiply a bunch of big fractions using the Java fork join pool framework. The first thing we do is we make a big fraction. We generate a bunch of calls to make big fraction, giving random numbers that are not reduced up to this maximum, and we collect all these things into a list of big fractions. So we have a list of very large, randomly generated big fractions up to this number, and that number is actually fairly large. The next thing we're going to do is we're going to create ourselves a function, a Java 8 function, that will reduce and multiply each of the big fractions. So the way this works is we take in a big fraction, one of the things in this list, and we first reduce the big fraction, so it'll become a reduced fraction, and then we go ahead and multiply it by some big constant. And that operation will then be used to burn a lot of CPU time. This is a very time-consuming operation because the fractions are gigantic, so it takes a while to run. And then we go ahead and we test 3 different variants of the fork join pool to demonstrate different ways to do this computation. So let's talk a little bit about that. So these are all helper methods that kind of wrap everything up into the right set of parameters. And each helper method uses a different means of applying the fork join framework. So this particular approach, apply all iter, uses a single loop along with work stealing to throw everything into one worker thread's deck, and then as it processes some stuff, the other threads in the pool will steal things from its deck. So this particular approach, as you see, is very simple to program, but it incurs a fair amount of stealing overhead because of the way it's programmed. You'll see when we look at that in more detail how it works. Apply all split uses recursive decomposition to disperse the tasks to worker threads in a more even way. So as you'll see, there's a lot less stealing going on here, but the program is a little bit more complicated to program and understand. And then the third approach we have here, which is called apply all split index, uses an optimized recursive decomposition approach to disperse tasks to worker threads. And the clever thing here is it doesn't actually end up copying the data. It just basically keeps all the data in one array, and then it uses indices to figure out which parts of the array to work on. So there are 3 different approaches with 3 different programming complexities, complications, and so on, and 3 different results. Each of the helper methods gets its own fork join pool. And as you may recall, if you say new fork join pool and you don't give any other parameter to the constructor, that will create a fork join pool that's sized to the number of processor cores. Okay, so that's the main thing I want to show you here with this particular example.